All right, so this is starting chapter 10. And chapter 10 is looking at what we call gas laws and how gases behave in terms of their forces that make them a little bit more interesting to study because they have less forces than other states of matter. So when we think of a gas, what are things that we could do to a gas that will change how they behave? So what are the factors or conditions that we could put gases under in order to change them? So hopefully you might have thought of volume, pressure, temperature. Most students usually think of temperature, but changing the volume, the pressure, so on and so forth. And the last thing we're going to look at is N, which is number of moles. Okay, so we have different relationships between these conditions. But first off, let's define pressure. So pressure is force per unit area. We talked a little bit about this in previous chapters, but now we're going to spend pretty much a whole chapter on gases alone. So we have some inverse and direct relationships depending upon the different conditions. So if I look at one condition or two conditions at a time, pressure times volume is going to be an inverse relationship. So as I increase the pressure, the volume will decrease. And if I increase the volume, the pressure will decrease. Volume and temperature are going to be a direct relationship. So if you think of a balloon, if I heat up that balloon, you're going to see the volume is going to change. So that is what we call a direct relationship. Pressure and temperature is also a direct relationship. So again, if I increase the temperature of a gas, you're going to see more particles moving at a higher force in the same area. So you're going to see an increase in pressure. And the other one is volume and number of moles. So this one, again, another example is the same as a balloon. You're blowing up a balloon, so the more air you put into that balloon, the bigger the volume is going to get. So please note that if you have an inverse relationship like pressure versus volume, you are multiplying those two to get to what we call a constant, If you have a direct relationship, that means you're going to be dividing one by the other. That's going to give you a constant as well. So you could do the same thing for pressure and the same thing for volume, okay? So direct relationships are always a proportion. Inverse relationships, you are multiplying those variables. What do the graphs look like? Well, if I look at pressure versus volume, it's a very famous graph. It's more of like a curve. And then volume or pressure versus temperature is going to be a straight line. Okay, that is what we call a direct relationship. Okay, so we could take each one of these individual, and we could have a gas law associated with it. There's Boyle's law, Charles's law, Gay-Lussac's law. We're not going to focus on that, and you don't need to focus on that as well. But there is one that you need to be aware of, and that's called the combined gas law. And this kind of helps you to remember all of the relationships. So if I take pressure and multiply it by volume and divide it by temperature, I'm going to get a constant, okay? So I could compare a gas in a container. I could change one of those variables, two of those variables, and I could see how it then is affected. So in terms of our discussions here, volume is going to be in liters. Okay, so it's going to be a capital L. What are some units of pressure? Well, we have ATM, we have millimeters of mercury, we have something called a torr, and K pascals, but we're going to kind of sidestep that one a little bit. You might have heard of PSI, pounds per square inch, in your everyday life, pumping up a tire. But we are really going to be doing ATM, millimeters of mercury, or torrs. For atmospheric pressure, 1 atm is the same as 760 millimeters of mercury and 760 torrs. Okay. And temperature is going to be in Kelvin. So it's capital K. And this is the one place in chemistry it needs to be in Kelvin. So before, when we were doing thermo and we were focused on the change in temperature, this one you have to have everything in Kelvin. So please remember, you're going to take Celsius and add 273 approximately to get your Kelvin. Okay, so I'm going to repeat myself millions of times, Kelvin, Kelvin, Kelvin. That is why you must always have your units in Kelvin. So no matter what the relationship is with temperature, sure, you go plug in 25 degrees Celsius. It just will not work. So just keep that in mind. So if I take a look at this combined gas law, and I include one more variable, okay? So the one variable I did not include was N. Well, actually, if I do include N, it becomes a particular constant. It becomes a particular constant called capital R. And what I'm deriving, or essentially not deriving, but kind of cluing you in on, is something called the ideal gas law. So this R value is 0.0821 liter atmosphere mole Kelvin, or you will see it as 8.314 liter kPa over mole Kelvin. So this is how you write the ideal gas law usually, is PV equals nRT. PV equals nRT. So I call it PIVNRT. Easy way to remember it. So pressure has to be in atmospheres or kPascals. Volume needs to be in liters. N is moles. R is then your R value, and T needs to be in Kelvin. So we could take this ideal gas law and manipulate it into some other equations as well. So I'm going to take PV equals nRT, and again, this is going to be the equation you need to know. Beyond this chapter, this is the one that we always refer to for gases, but I can manipulate PV equals nRT into another form. So I could take moles. I know moles is grams divided by molar mass. That's how I could find moles, is taking grams divided by molar mass. And I can put that into this equation. I could put that into this equation. So I could take P times V is equal to grams over molar mass times R times T. So what I can do is then take the molar mass and bring it over to the left, and then I can bring the PV to the right. So molar mass of a gas is equal to the grams of the gas times R times T divided by its pressure divided by its volume. So this is one equation that is very useful in a couple different places. If you do not know the molar mass of the gas, or if you do, you can then calculate other things. The other equation I want to derive has to do with the density of gases. Now, we talked about density really early on, mostly about liquids and solids, but density of gases are always grams per liter. Mostly because gases, those particles are very far spread apart, so it's much easier to do things in liters. So if I take a look at this expression here, grams is on top and volume has to be in liters in order for the ideal gas law to work. So if I could substitute that in here, I could rewrite this equation as molar mass is equal to the density times R times T divided by the pressure. So I could actually use either one of these equations for a couple different applications. All right, so that is one gas at a time. Okay, one gas at a time. So what about if we have what we call mixtures? So what if I have mixtures of gases? Okay, so that's what this page is going to be about. So what if I have 3 gases in a container? Okay, and in that container, they're going to have the same volume and the same temperature. So the only thing that's really going to change there is going to be the pressures. We have Dalton's Law, and Dalton's Law says the pressure, total pressure in that container is due to however many gases, individual pressures you have. So what we're going to focus on especially is when we do some experiments is we are going to be taking gases and collecting them over water. So a big focus of Dalton's law is going to be the fact that we're going to have to subtract out water vapor sometimes in order to calculate what the pressure of the gas is. So I'm going to derive something for you. So I'm going to pause the video and then you're going to see my notes from there. All right, so Dalton's law, if we take the ideal gas law, okay, so, and we just have pressure on the left, I have nRT on the top and V on the bottom. So if I want to look at the total pressure in the container, I need to look at the amount of moles of each one of the gases. So N1, N2, and N3 is the number of moles of each individual gas. So that's what we call the NT. So that's the total number of moles. R is going to always be a constant. Temperature and volume are going to be the same in a container because you're talking about the same container. So if I were to take a look at each individual gas, I could compare it to what I call the total. So if I take the pressure of gas 1, that would be the number of moles times R times T over volume, versus my total pressure, which would be number of moles total R, T, and V. Well, if you look at this setup, what cancels? Well, the volumes cancel, temperature cancels, and R cancels. So what do you have a relationship between? You have the relationship between the pressure and the number of moles. Okay, so what I can do is I can calculate something called a mole fraction. So this is a capital chi, I think is the symbol. It's a weird looking X, capital though. The pressure of each individual gas versus the total pressure is always going to be proportional to the amount of moles of that gas versus the total moles in there. Now this is going to be a fraction, it's going to be in a decimal form, and you're not going to have any units associated with it because essentially it's moles over moles or pressure over pressure. But what you're going to use this for is you could use it to find the individual pressures in the container. So if you know how much you have of each one of them, you could take the mole fraction and multiply by the total pressure and you could get the individual pressures. Or if you know the individual pressures, you know the total pressure, you could find the mole fraction. So that is why it's a very valuable derivation essentially of Dalton's law. Even though it seems a very simple concept, it's very useful in a couple different applications.